Hey everyone, and welcome to this explainer. Today we're going to peel back the layers of a classic computer science problem. We're starting way up high with the algorithms, and then we're going to dive deep, right down into the actual memory mechanics. So whether you're gearing up for a tough technical interview or you just love figuring out how data structures actually work under the hood, you are definitely in the right place.
So let's just dive right into it with a fundamental challenge, one that really tests how well you understand data structures and ordering. The premise sounds incredibly simple, right? You're handed an array of numbers, and you just need to replace every single number with its relative rank. But as soon as you throw in negative numbers, massive gaps between the values, and, most importantly, duplicate elements, well, things get really complicated really quickly.
Here is our roadmap for today. We're going to start with the array ranking problem, then move into discretization and binary search. After that, we'll look at mastering search boundaries, explore hash maps and sorting, dive under the hood into linear probing, and finally wrap it all up with complexities and final takeaways. Let's get to it.
All right, Section 1, the array ranking problem. Because honestly, it's pretty much impossible to build a solid algorithm if we don't understand our exact constraints first.
So the rules for array ranking are actually pretty strict. You always start at 1. The order dictates the rank size, and duplicates absolutely have to share the exact same rank. Plus, the ranks need to be tightly packed together. To put that into perspective, even if your input array contains the numbers 10 and, say, 1 million, if they happen to be the two smallest unique values in the entire array, their ranks will simply be 1 and 2. No gaps allowed.
And this perfectly illustrates how these rules play out in practice. It's really cool to see how duplicates just compress into identical shared ranks. Look at the first example. 10 is our smallest number, so it gets rank 1, and 40 is the largest, getting rank 4. Easy enough. But check out that second example. An array of 3 100s simply becomes an array of 3 1s. That duplicate rule is exactly why we can't just get away with doing a naive comparison of every element against every other element. It just wouldn't work.
Moving right along to Section 2, discretization and binary search.
This brings us to a seriously beautiful concept known as coordinate compression. Basically, this allows us to shrink a massive sprawling domain of values down into tight, manageable ranks. Imagine you're looking at a huge sparse map of coordinates, and you just want to shove them all together so they sit right next to each other. But, and here's the catch, without changing who is to the left or right of whom. That is literally exactly what we are doing with our array values here.
The steps to actually pull this off are just so elegant. First, you deduplicate the array. Then, you sort it. Finally, you binary search that sorted list to instantly pinpoint any element's rank. By stripping out the duplicates first, we're basically creating a pristine, perfectly sorted lineup of unique values. So when we binary search that lineup for our original elements, the position where we find the element naturally acts as its rank. It's such a brilliant way to separate the ordering logic from the remapping logic.
But to make that binary search work flawlessly, we really need to master Section 3, mastering search boundaries. Because as it turns out, not all binary searches are created equal.
Now this is super interesting. There is a critical distinction here between searching for whether an item simply exists versus searching for its insertion boundary to get a 1-based rank. If you're coding in Python, you'll know this is the difference between bisect_left and bisect_right. Or if you're a C++ developer, it's lower underscore bound versus upper underscore bound. When we use the correct boundary, the upper bound, it tells us exactly how many unique elements are less than or equal to our target value.
So, here's your pitfall alert. You've got to watch out for this. It's a massive developer gotcha. Using the wrong boundary function will completely break your ranking logic. If you use a standard binary search that returns a 0-based index, you're going to find yourself writing a bunch of messy edge case code just to add 1 and handle duplicates manually. But by intentionally choosing the upper boundary search, the math just effortlessly works itself out.
All right, let's pivot over to Section 4, hash maps and sorting. I'd argue this is probably the most common pattern interviewers expect to see for this problem.
Think about it. Instead of doing a binary search every single time, we can just map our sorted, unique values straight into a hash table. This lets us reconstruct the array with lightning-fast lookups. We still sort the unique values, sure, but we only have to iterate through them once. We assign rank 1 to the first value, rank 2 to the second, and we store those pairs right into our hash map. From there, we just loop over our original array, ask the hash map, hey, what rank is this number, and replace it. Those constant time lookups make the final transformation incredibly snappy.
But you know, how do those O of 1 lookups actually work physically? Like down at the hardware level?
Let's pull back the curtain in Section 5, Under the Hood with Linear Probing.
It's honestly crazy to look at the historical timeline here. This foundational technique has evolved from way back in 1954 straight into the core of our modern computing architecture. Linear probing is basically a method for resolving hash collisions, which is what happens when two different keys try to shove themselves into the exact same memory slot.
This quote right here perfectly captures why we're even talking about this. Linear probing isn't just some textbook theory. It is the undisputed king of real-world hardware data structures. Modern CPUs are heavily optimized for reading memory sequentially. So an algorithm that aligns with how the physical hardware actually wants to read data, that's always going to win in a production environment.
You can think of linear probing kind of like a crowded parking lot. If your designated parking spot is taken up by a collision, what do? You don't perform some complex mathematical operation to teleport to a different floor of the garage, right? No, you just drive forward to the very next available open spot. That simple concept is what we call open addressing.
And because it scans memory sequentially, it is incredibly cache-friendly. But you do have to be aware of something called primary clustering. This is where one collision causes a massive traffic jam of subsequent collisions. See, when your CPU fetches a memory address, it prefetches the adjacent addresses into its ultra-fast cache. Linear probing takes perfect advantage of that. But if your hash map gets too full, meaning the load factor gets too high, those little traffic jams merge into massive clusters. Suddenly, your lightning-fast lookup degrades into a painfully slow sequential crawl.
Let's bring it all together now in Section 6, Complexities and Final Takeaways. Understanding both the algorithm and the physical constraints gives you a huge advantage.
So looking at the big O, both of our high-level approaches hit the exact same bottlenecks. They are completely dominated by the O of n log n time required to sort the array. You just can't get around that global ordering requirement. To know a number's rank, you absolutely have to know where it stands relative to everything else. And both approaches require O of n auxiliary space to store either the sorted unique values or the hash map itself.
So when you're choosing your tool for the job, keep this in mind. Sorted vectors offer sheer memory efficiency and locality, while hash maps trade that memory space away for pure speed. For really small arrays, standard arrays with a binary search, or heck, sometimes even a linear search, can actually outpace hash maps simply because they avoid the overhead of computing hash functions and dealing with collisions entirely.
To wrap up this explainer, I'm going to leave you with a massive system design question to chew on. We've talked a lot about caching and linear probing in RAM today. But what happens when you have terabytes of data? How do you sort and assign ranks then? Take what you've learned here about coordinate compression and memory mechanics and try to apply it to a distributed world. It's a real brain teaser. Keep learning, and I'll see you in the next explainer.